It's a pleasure to have Professor Hossein Yavartanoo, who is going to talk about physmatics, the tip of the iceberg.
Okay, thank you very much for giving me a chance to speak. It's a big challenge to talk about it to this audience who are mostly mathematicians and all are very expert on what I'm going to discuss. Yet I accept the challenge because I'm hoping to learn something through discussion. So please, okay, first comment is please stop me anywhere you feel that I'm saying something wrong or you need to give me, let me learn something. So please stop and give comments. The second comment is, I'm not going to show you any formula. I will show you very few, but these are far from being precise. A reason is what I'm going to discuss is not completely understood or developed yet. So please don't take it as some well-established mathematical structure, but these are some ideas and inspiration. So please leave aside your rigorous mathematical head for next 45 minutes. Okay, with that warnings, let me start. Physics and mathematics are very closely related subjects. They're basically born together and grew up together. And they were actually the same subject until rather recent years, let's say 18th centuries. In a way that any great discovery that you take from the history either was some mathematics for understand the nature or some mathematics was inspired by some phenomena in nature. Here are very few examples of my interest. Any great discovery in past you take, by past I mean before 18th century you take, is an example of what I'm trying to claim here. A few of my favorite is interesting work of Pythagoras of studying the symmetries of Platonic objects. They are trying to relate this of 5 Platonic objects to 5 fundamental elements that.
I don't know that there is a mistake in the morphology. The solid, three-dimensional
okay. Yeah, plot. Right. What is in? Right. Yeah. Yes. But what I was trying to say is studying the symmetry of these objects, which are some discrete subgroup SO3, or let's say discrete subgroup SU2, is still interesting, even though the connection to 5 elements doesn't make any sense. But I will show you some interesting things in very modern application of these studies. Another example of my interest, maybe more relevant one, is the work of Omar Khayyam, who was trying to make a very precise calendar. In order to make the most precise calendar possible with that time of devices, he has to compute as accurate as possible the period of the Earth around the sun. And for doing that, he had to discover lots of interesting mathematics. This includes solution of quadratic and cubic equation, binomial expansion, and so on. Another example, another favorite example of mine is the discussions of Galilei in arguing why heavy and light objects should, if we ignore the air resistance, should fall the same. You see that he was a true scientist. He was not experimentalist. He had argument for that experiment that he has done. And in this argument, you see lots of interesting mathematics, symmetry, and proving by contradiction. So this is a very nice example of how the mathematics helps the physics and vice versa. And of course, the interesting example of most of us is the great work of Newton in discovering the calculus in part. And that was for understanding the dynamics. So you see that something which is very natural, something we see in all every day, every second of our life, motion. To understand it properly, we need a lot of deep mathematics, calculus, differential equations, and so on. The situation was more or less the same until 18th centuries or beginning of 18th centuries, what happened that time was mathematics started to grow very fast. Lots of abstract ideas appeared that didn't have an apparent or immediate application of understanding the nature. But the connection was still there in a way that any great discovery of physics was still based on mathematics, or the language of describing this discovery of physics was based on language that have been developed earlier by mathematicians. Of course, not all mathematics that time had application to physics, but the connection from one side to the other side was still the same. What I want to say in this slide is, even though for this old question, for this some classic subjects, there are still problems that to understand it properly, we need lots of modern mathematics. Some of these examples have been very nicely reviewed a few weeks ago by Lars. Among them, one of my favorite one is something in physics seems very intuitive, very simple, that energy is positive, more precisely, positive energy, positive mass theorem. And you know that for a proper understanding of this, we need a lot of sophisticated mathematics that have been shown by Yao and his students through several nice papers, some others. This is one example I like, that to get understanding of something seems very simple in physics. Well, okay, yeah, they were physicists, but still, I'm saying that the proof of but still, there are lots of nice mathematics in this paper. So now I want to argue that something interesting happened last 3 decades in studying physics. And this is some ideas in physics are start influence deep mathematics. And that's what people call it physical mathematics, comparing to mathematical physics, the old term. Now they are calling physical mathematics, or in short, physmatics. So physmatics are ideas of physics which influence some mathematical discoveries. And I'm going to show you a few examples. Any complaint so far? Okay, my first example, or first few examples, are dualities. Dualities arise in physics when two different aspects of nature, which are apparently look very different, are related to each other. Or to be more precise, they are the same. A few examples that I'm sure all of you are familiar is electromagnetic duality. Or if you're doing statistics, you may be familiar with a few dualities in Ising model. Or if you know field theory, there are many examples. Field theory, there are a bunch of it in a string theory. And, some rather recently discovered ADS-CFT. My main emphasis will be some dualities that we see in string theory. So in physics, when we have two apparently look like different systems, and when the duality is the relation between two look like different systems, the states of two look like different systems, which this relation is respected by dynamics. So we have a one-to-one relation between states of one theory to another theory, and this is not just for one slice of time, but in all time we have this. So this is called the dual system. I don't know how to define it very properly, very precisely in mathematics, but let me give it a try. Let's say duality are highly non-trivial isomorphism, or in a way that they are connecting two different, even look like different mathematics. Some subject of mathematics to another subject are. Okay, so dualities are some sort of quote unquote isomorphism between different objects in mathematics. So to be more precise, we have a theory described by some of its parameter. This can be discrete number or continuous. And roughly speaking, they form a manifold. We have another theory, totally look like different, with the different parameters. And these parameters, roughly speaking, form a manifold. And these two manifolds, surprisingly, are the same. There are some observations there are some observable in this theory, which are non-trivially mapped to the observable of the other theory. That's, let's say, this is what duality means to us. To give you an example of what these parameters are, for example, this can be some discrete values, like the choice of a string theory, view of them, or the topology of the target manifolds, or some structure that we put by hand on it, like the metric or the connection and so on. But the other one can be other string theory, other different topology, different metric, different everything. Yet we, by some physical argument, we believe that these two must be somehow related, must be the same, or different aspects of the same thing. So observable in one theory, which we denote roughly by this one, are related to non-trivial map to the observable to the other. So by that, I'm not trying to say that there are two different things which are somehow related, but I'm trying to say that these are different perspectives of the same thing. So basically, these are some shift in perspective. These two systems are the same. So in other words, these two are indistinguishable. It's important because this tells us neither of them is more fundamental. These are coming with the same right. Okay, so I'm sorry for this interruption. So where were we? So as I said, having this duality means our perspective of what the question is even changed. So instead of solving, just emphasizing of solving a problem, we should indeed find the best dual description of the problem to solve it. This is another message of these dualities. And the most important thing, if we take these dualities, which most of it are conjectures, seriously, it tells us that many of our intuition regarding to the, I don't know, dimensions of a space or topology of a space, or even what we call quantum behavior, what we call it classical behavior, or what we call it fundamental particle, what we call it composition. These are all depend on which duality frame we are choosing. So these are not fundamental things to describe the nature. These are, and this is very counterintuitive, saying that a space-time dimension is something not fundamental. You cannot distinguish between situation with, let's say, 5-dimensional, 4-dimensional theories. So these are not frame independent. We know the loss of our very natural intuition by any discovery failed. For example, when we know that the Earth is not flat, then the very natural concept of what is up, what is down fails. Or by discovery of relativity, what we always thought is very absolute, like what is space, what is time, also fails. This one? This is particle, this is wave. So another very counterintuitive discovery to come with quantum mechanics is what is called particle, what is called wave is also there is not very fundamental things to consider. So for those who are familiar with special relativity, I would like to borrow this this terminology of inertial frame to use the word of duality frame. So by duality frame, I mean using one perspective of this So roughly, this is the situation. So we have a theory. This theory has a moduli, and this moduli has some boundaries, some corners. It turns out in each corners, the physical system may look totally different. For example, in one corner, we may deal with the dynamics of strings. So we are basically dealing with the Riemann surfaces embedded in higher dimensions. In one corner, we may deal with particles. So we're dealing with a Feynman diagram. In some corners, we don't know what it is, and middle, we don't have any control on it. In some corners, if we're lucky, we may be able to define what we want to compute. And if we are very lucky, we may even compute some observable. And among them, some of them, of course, not all, some of them are duality frame invariant, in a way that I can extrapolate the result from one boundary and going to another boundary, and then comparing these two totally look like different things. So this is what duality means. Let me take an example. It's the best example. Sorry, this slide doesn't show well. My next example, the first example in these dualities is mirror symmetry. So mirror symmetry is a statement on Calabi manifold. Calabi manifold, by Calabi I mean a Kähler manifold, complex manifold with a Kähler structure, which had with trivial canonical bounding. What is very interesting about this type of manifold for us in physics, coming with a theorem that has been proved by Yao some years ago when we got fields method for it. And that's these admit Ricci flat metric. That's very important by several reasons. First of all, if we want to study the lower dimensional physics through the string theory, we can compactify the higher dimensional theory. And in the lower dimensions, we get the flat, we get no cosmological constant. So that's also preserves some supersymmetry. So we have good techniques to study the theory. And the other things come from the fact that these are complex variety, and we can use techniques of algebraic geometry, even without knowing what is the metric on this manifold. We can still do computation, the relevant computation for this studying lower dimensional physics. So this is another place where very abstract mathematical ideas come to have a very physical system that we want to study. As I said, mirror symmetry is a statement of duality between two apparently very different Calabias. By different, I mean they might be even topologically different. So this is totally non-trivial statement that these two Calabias are somehow related. So more precisely, this is relating the Hodge number PQ to n minus p. Let's say the complex dimension is n minus p and q. So it's like, if you look at the Hodge diamond, it's like we put a mirror, 45-degree mirror. So for example, if you look at H11, it's related to Hn minus 1 and 1. So H11 is the dimension of the Kähler module. Or more precisely, this mirror symmetry, this statement maps some sort of deformed, complexified Kähler module on one Calabia to this one, which is the dimension of the complex module. So it's related, these two to each other. I'm not going to review his story. This is a very incomplete, very partial, very personal list of some interesting things happened during 1988 to 1994. Some evidence have been observed by people who were studying 2,2 conformal field theories that the target space is the Calabi. They got some hint of some possible connection between these two. I think the first example was observed by Brian Greene, who was working on Gepner models, special two-dimensional CFTs. A large number of the other example, I think, studied by Candelas. Another interesting thing happened at the same time was introducing topological strings by Witten. It's a topological version of a string theory, even though topological, but it's still quite interesting. So it has non-trivial observable. And the statement of the mirror symmetry is a statement of duality between what they call A model and B model in topological strings. Another version of it as a duality between two derived categories, which is called homological mirror symmetry, have been introduced by Konstantin. Another thing he done was revisit the construction of the Candelas, counting the rational curves, and express it as a precise mathematical conjecture. In a series of papers in great detail, Yao and his students proved this conjecture. And this is a starting of a great discovery of lots of interesting mathematics and physics since that time. It's a very active subject. There are thousands of interesting papers have been written. You look at arXiv. Last year, there were more than 300 papers, basically. Every day there is a paper on this. There are lots of interesting conjecture in both sides, in physics and mathematics, which are deeply related to each other. So proving one is very helpful for the others. Give some comments about it later. So as I said, a statement is the relation of counting the rational curve on one side and relating to some period integral to the other side. So you see that this map two different types of mathematics. Here you are doing algebraic geometry, so very difficult question in general algebraic geometry, to some question in complex geometry, some rather easy questions on integral. These two totally different look-like mathematics are related by this physical idea. So this, through the physics, this subject of mathematics is somehow mapped to the other subject of mathematics. And interesting thing is, one side is very difficult, while the other side is easy. So you can use one side to learn something about the other side. What else I want to say? Because of course, this is just one example of what mirror symmetry says, or to be more precise, is genus zero of mirror symmetry. There are infinitely many things you can compute this side, in principle, and infinitely many things you can compute the other side, and you can map these two. Again, another interesting example that where physics come to this story is through what we call in physics T-duality, another very bizarre duality in physics. It says the nature of, let's say the universe is a cylinder with radius r. It says it is indistinguishable with the universe with the radius 1/r. This is very bizarre statement. And it is true because the fundamental object of theory is not point-like. Otherwise, of course, it was very easy to measure it and say this is different from the other. But these two are identical. I'm not saying related, these are identical. And this is very non-trivial consequence of the fact that the fundamental objects are strings, and through this map, there are those who are wrapped around this and those who are not are interchanged. So the way the different corners of that moduli space are related by this duality, this red line. The blue line is something even more interesting, but less understood. So I'll talk about it. The way it comes to a story, this physical phenomena, this physics come to a story, is there is very close relation of what I told you with something in algebraic geometry, Fourier-Mukai transform. So in an interesting work some years ago, Strominger, Yao, and Zaslov had another statement for the mirror symmetry. Let's take this Calabi to be some n-dimensional real base times torus. It's not a direct product. It's like a fibration, a very non-trivial fibration. Torus on this n-dimensional real base. And using this Fourier-Mukai transform fiber by fiber, then you can construct the dual one. You see that again, well, this is a conjecture, and the non-trivial part of this conjecture is this is not direct product. Otherwise, it was very easy to. It's just if it was direct product, it was just a statement of triviality. It's non-trivial and singular vibration. So you see, this physics ideas gives us very nice geometric interpretation of what this bizarre duality is in Let me skip this example. This is a very nice one. I wanted to tell you something about this, but maybe in private I can. My next example is quantum black holes. This is another place where the physical ideas influence the mathematics. This is perhaps the best key we have currently to understand what quantum gravity is. So the status of studying quantum aspects of black hole is very similar to the status of studying black body radiation 120 years ago. And, people were trying to understand what quantum mechanics is. Many ideas in mathematics and physics are somehow passing through this quantum black hole. So I want to invite you to do one experiment at home. I don't know, maybe at your office. As I said, there are internal direction in a space. For very simple example, let's say a space-time is 5-dimensional, and the internal part is also 5-dimensional. So take this 5-dimensional internal part of a space to be very simple manifold. Let's say 2-dimensional Calabi-Yau times S. So it has some non-trivial large cycle. In the theory, you have some object, extended object, like here in this particular example, you have 1-dimensional object, 1-dimensional extended, or 5-dimensional object, and try to wrap those objects in the minimal circle of this Calabi-Yau. What is important about this object is they have tension. You stretch it, it has energy. So when you wrap them, it's like you are putting energy on the space-time. And remember, this is just from 5-dimensional point of view, it's just a 1 point. So you are putting lots of energy in 1 point of a space. What do you think you will get? You are putting lots of energy in 1 point. You're putting lots of mass in 1 point. Black hole, singularity, black hole, you get a black hole. So this is how you can make a black hole at home. And well, I simplify the experiment a lot. Indeed, you're doing this experiment in 2 duality frames. One duality frame is what you can play with these branes and cycle. The other one is the duality frame where you're dealing with supergravity. So you're solving the Einstein equation, checking the Ricci-flat condition, and so on. So on the other frame, indeed, you're getting the black hole. And now I want to ask a question. In how many different ways you can do that? Giving you a certain number of this 1-dimensional and 5-dimensional object, how many different ways you can do that? Or be more precise, these are some minimal cycle. So you can study the moduli of this minimal cycle. I mean, you can study the cohomology of this minimal cycle and counting the dimension of this cohomology. Or in the index version of it, you compute the Euler class. What do you get? Well, you can compute it if you know algebraic geometry. This is a straightforward exercise. And the answer was predicted 50 years ago by 2 gentlemen, Hawking and Bekenstein and Hawking, 50 years ago. What you get is the area of something, we call it horizon, which if you ask what is this horizon, go back to the duality frame, the second duality frame that I told you, where you have to solve Ricci-flat condition. I give you the symmetry of this problem. It's a spherical symmetry. You solve the Einstein equation, and the solution is something we call it black hole. There is a null surface in this solution. You measure the area of this null surface, exponentiate it, and you will get the number of this dimension of this cohomology. That's another very interesting influence of ideas from physics to mathematics. So to be more precise, let's take the number of this 5-dimensional object to be Q5, the other one-dimensional to be Q1, then M and N are these. So basically, you have to compute a elliptic genus. Taking a given, for a given M, you compute this, and you will find that number you were looking for. So you see, in a very non-trivial way, algebraic geometry and differential geometry are connected through the black hole. That's another example of what I call it Physmatics. And as you see, as you're dealing with the modular form, it's naturally connected to the theory of modular form, whatever related to the theory of modular form, including, I don't know, everything in number theory is somehow one way or other related to modular form, or some other things like, let's say, 3-dimensional topology to the, what is it, Witten, Reshetekin, Torayev, related to the studying of modular form. What is modular form? There's some function with some nice property under modular transformation. You see, this is somehow quite restricted. If k was 0, that was very, very restrictive. But for given k, let's assume that k is integer or half integer. It is still quite a strong requirement. Strong that these functions are very rigid. Indeed, the ring of this modular form is just can be just right in combination of two Eisenstein series. So somehow the dimension is finite. And the power of this modular form is coming with this very rigid structure. So in some sense, if you Fourier transform it, if you know very few copies, you know all information about them. I'm sure anyone who studied quantum field theory are familiar with some of these modular functions that appears in, say, partition function, torus, and so on. Or I'm sure all of you have seen the application in, let's say, finding the generating function of partition of integer. That's very nice story of where this modular form appears. Or some sort of fermionic version of this story also include this modular form. And you guess that it again appears in studying black holes. The question is, you have some mass and you have some statistical physical system. You put this mass and you want to know in how many different ways this energy or this mass is distributed among these microstates. Well, I simplified the question a lot, but this is basically what we are computing in many cases. And if we were able to compute this degeneracies, let's call it this d micro, we expect that if we take the logarithm of this through the Boltzmann argument, we get what is the entropy of the corresponding object. And through the Wittgenstein and Hawking, we expect that the first term behave like to be proportional to the area of the horizon. And what you get from that string theory exercise was exactly the same number. It's not just you get something proportional to area, you get exactly this coefficient 1/4g. So this is very, very non-trivial evidence that string theory has something to do to quantum gravity. It's not the end of the story. You can expand this and you expect the other terms. And well, if you call it a strong evidence, the next thing I'm showing you is a magic. For examples that we can compute this in a string theory, turns out that we can get the next coefficient, the next terms with all correct coefficients. That's the magic of string theory. So this is one simple example of where we can compute this d micro, and we are ending up with some modular forms. And the different terms, you see that is coming with exactly the correct number as expected from computation from gravity side. That's very highly non-trivial test of a string theory. Another example is, my favorite example is my proposal, and along with the colleagues, we call it horizon fluff. That's once again in computing the degeneracies of a black hole, a three-dimensional black hole. We are dealing with some modular form. This is the partition of this large number. And again, we get the correct number for the Bekenstein-Hawking term and the correct number for the logarithmic correction, so on. So one mathematics question, and then I was sorry for going over my time. So as I said, computing this is a very difficult job, even in string theory. There are very few examples that we can, using different techniques, we can compute this. Now, I ask this question, assume we take some of these and Fourier expand it. What do we get on the left-hand side? For the example I showed you was modular form. You may ask this question, what about the other example? What is the modular properties of this function we get in this way? Very interesting thing was, for another example that we can compute, quadro BPS black holes on compactification of type 2 on K3. If you do this exercise, you can see that by taking appropriate parameters here, you can generate all known Mach modular forms. You can even do more. You can change it and generate even more, infinitely many other Mach modular forms. That's another place where some nice ideas of physics give us some interesting results in mathematics. Or the other example is 1/16 BPS in ADS5 lambdas 5 is related by this way, is related to Eisenstein series, somehow related to what people call it a quantum modular form. Let me stop here, showing you one quote of Boltzmann, which I think is quite relevant considering the current status of string theory. Thank you.
Any questions? Nicola. That's a
I was just wondering if this reference was done in Berkeley or when he was back in
this one?
Austria, yes.
I think it was the last year of his life.
He was in Berkeley just before this.
But he passed away in Italy, right? In Trieste. Yes, yes.
But he was in Berkeley, I think, in
might be
1904.
Yes, might be.
So I was asking. So this is from.
I think it is 05, if I'm not mistaken.
Okay. Thank you.
So I would like to ask you a couple of questions.
So I think Lars also wanted to ask something.
Sorry, this is Lars.
Yeah, I just wanted to comment on this when you mentioned these various dualities and so on. And I mean, many of these that you mentioned are kind of, and I don't want to antagonize anyone, but I mean, many of those are kind of heuristics in some sense.
Conjecture.
They're conjectures,
sure.
and sometimes they lead to studying these conjectures lead to new mathematical developments like mirror symmetry. But I mean, some of those are kind of you know, running. You know, I think you can say honestly running into problems that the original conjecture or heuristic
sure.
has been modified, and not just once, but continuously, so to speak.
Sure.
So I think it's important to distinguish between when we talk about these things, to distinguish between sort of precise, definite, even conjectures and kind of, heuristic
Definitely,
metaphors.
definitely. That's why I bring the mirror symmetry as the first example. This is the only example I know that we can rigorously define what conjecture is. For the others, I don't know if we even know what conjecture is. Mathematically precise question is not even known. That's true.
Yeah,
Thank you.
I think it's important to
Sure.
bring that up.
Sure. Thanks.
More questions? I would like to ask you some questions. One is, in this result of Strominger and Hawking, that
Strominger
you're
and Hawking?
calculating this partition function for the black hole.
Strominger bound for you.
Yeah, and then you're saying that is actually related to something on the horizon. Is that quantum?
Yes.
Strominger-Vafa. Is that quantum gravity, or is that just quantum field?
Well, I showed
What
you.
is the dimension of that black hole? Is it supersymmetric, higher dimension, or is it
As I
normal?
Well, I simplified a lot. As I said, the exact experiment is in two different duality frames. In one duality frame, you can work with this extended object, and you can put them, they don't interact. It means you turn off the gravity somehow. But the result of this computation, thanks to the lots of supersymmetry, is preserved. So you can extrapolate the result to the regime where the gravity is strong. So you're dealing with real black hole in supergravity. And the computation you have done in this string theory, highly stringy corner of the modular space can be extrapolated to where you can trust the supergravity computation. And that's how you can.
But that particular result, that the partition function has to do with area of the horizon. What's the
first term
of that black?
You see that when you expand,
it is quantum. I see. Right. Okay.
Exactly. This whole term is quantum gravity. The first, you can expand it and say, okay, this is the classical part.
Okay, one naive other question. So in algebraic geometry, when you count what you call the string worldsheets, for us is algebraic curves inside some ambient variety. One thing that happens because of the symmetries of the underlying ambient variety. For instance, when you're counting things on surfaces, algebraic surfaces, count of curves on algebraic surfaces often exhibits modularity property. If you're counting curves, algebraic curves, for you it would be D2, D0 branes. In a quintic threefold, partition function of that thing is absolutely not modular. So I want to understand, how does the physicist understand this? But for us, if I want to count curves in a quintic threefold, and there is a conjecture by a physicist saying that the partition function you're counting is a Mach modulo form, I would immediately think, based on experience, that probably these curves are lying on some divisor inside this threefold, which is an algebraic surface. And that's in fact the conjecture of Strominger, Gayotto, Yin on the modified elliptic genus. What is the physical reason? How do you see this modular property? Is there some physical justification? Like I haven't seen modular count for things counted inside the threefold.
Well, I don't have the complete answer to this question. Maybe it is related to the question of partition. You have the amount of the, let's say, the mass, and you want to divide it into, I don't know, D5,
so
D1.
Mathematically, it has to do with the symmetries of the Hodge structure of the variety in which you're counting things. That's what mathematicians sees it that way. You know. Yeah, so that's actually a good example. So over there, for us, that would be count of algebraic curves on the K3. That's absolutely modular. Yeah. But I'm just saying, from physics, I never understood how does the physicist actually predict modularity. That's what I'm asking.
So your question is how this modular form manifests itself in this computation?
Yeah, like something like, okay, maybe this partition function is entropy of some kind of a black hole. For such and such physics reason, I'm expecting modularity. Something like that.
Well, I don't know the answer, but
And this is for example, you get that.
but those are very
General of the example you can walk.
Okay.
But those are very simple examples. You're referring to toroidal compactification, right? Computing, I don't know, some topological partitions. There, it's clear where this modularity comes from through this topological partitions you are computing. But in general case, I don't really know how this, Mach modularity, for example, or Eisenstein series appear.
They claiming that
Okay.
but if you are you are
Okay.
situation of the
Any other question? If not, let's thank you.